Picture a modern city skyline, a metropolis of steel and concrete, dominated by towering glass structures. These architectural marvels are the heart of our urban lives, but they are also immense consumers of energy. What if we could fundamentally change that relationship? Imagine every single window, every glass facade, not just letting in light, but silently harvesting its power. This isn't science fiction. This is the dawn of transparent solar technology, a revolutionary approach that turns our buildings from passive structures into active power generators. For decades, solar power has meant bulky, opaque panels on rooftops. While effective, this approach has limits, especially in dense cities where rooftop space is a commodity. The vertical surfaces of skyscrapers offer exponentially more area. Transparent solar technology seizes this untapped potential. Instead of compromising a building's appearance, the windows themselves become sophisticated power plants, blending so seamlessly into the architecture they are virtually invisible. It's a paradigm shift, energy generation that is integrated, not just added on. The implications are staggering. We're not just talking about a single building reducing its carbon footprint. We're talking about transforming entire cities into vast distributed energy networks. Each skyscraper becomes a node in a resilient, decentralized grid. Buildings could meet their own energy needs and feed surplus clean electricity back to the community, reducing the strain on traditional power plants. This creates a more stable, secure energy future where our cities don't just consume power, they produce it, right from their very skin. And this isn't a distant dream confined to a lab. The fundamental science is proven, the engineering is elegant, and the materials are being manufactured at scale. Years of breakthroughs in materials science and nanotechnology have brought us to this tipping point. But it begs a fascinating question. How do you create a piece of glass that is clear enough to see through, yet sophisticated enough to capture the sun's energy? How can something be both a window and a solar panel? To understand this marvel, we need to look closer. We'll peel back the layers of this incredible technology, from the specialized glass substrate to the ultra-thin photovoltaic films that selectively absorb invisible light. We'll explore the different scientific approaches and see how these power-generating windows are built, tested, and installed in buildings today. This is one of the most exciting revolutions in clean energy, and it's happening now. The future of our cities is about to get a lot brighter. Let's pull back the curtain. Transparent solar panels aren't perfectly clear like picture glass. They're engineered to be spectrally selective. They let most visible light through, but capture energy from invisible ultraviolet and infrared rays. The key is balancing three things: visible light transmittance, AVT, color accuracy, CRI, and clarity haze. High AVT means rooms stay bright and welcoming. High CRI ensures colors look natural, not tinted or distorted. Low haze keeps the view crisp and clear. The challenge? Absorb invisible light for power, let visible light pass, and keep the window looking and feeling like glass. Engineers are solving this puzzle, making solar windows that are nearly indistinguishable from regular ones. The result? Energy-generating windows that don't compromise on beauty or function. That's the magic of transparent solar. Let's see how it's done. The quest to turn our glass-filled cityscapes into power plants has sparked a wave of innovation. There's more than one way to make a solar window. Instead of a single solution, scientists are pursuing several distinct pathways, each tackling the challenge of balancing power generation with transparency. Organic photovoltaics, or OPV, use printable, carbon-based inks. These special polymers are tuned to absorb invisible ultraviolet and infrared light. This allows visible light to pass through, leaving the window perfectly see-through while it quietly generates power from the unseen parts of the spectrum. Perovskite solar cells use crystal structures that are thin, highly efficient, and can be made semi-transparent. Their main challenge is durability, as the crystals can degrade when exposed to moisture. While their potential is enormous, research is focused on improving their longevity for real-world applications. Luminescent solar concentrators embed dyes or quantum dots in the glass itself. These particles absorb light and then cleverly funnel it to hidden solar cells mounted on the edge of the pane. This method also opens up unique aesthetic possibilities with colored architectural glass. Micro-aperture thin-film solar uses ultra-thin strips or a grid of tiny, opaque solar cells. The pattern is so fine that from a distance our eyes perceive the window as transparent, a clever optical illusion that generates power. Each approach balances transparency and efficiency differently. The more see-through the window, the less energy it can generate. But as these technologies rapidly advance, that balance is constantly improving, making solar glass more practical and powerful every year, with a seamless and beautiful integration. So what do these layers look like? Let's look inside one. A solar window is a high-tech sandwich of ultra-thin layers. It starts with flawless glass, then a transparent conductive oxide, a TCO layer like indium tin oxide in lab deposition. Next comes the active layer. It absorbs light and makes electricity, organic inks, perovskites, other photoactive materials. Electron transport layer guides electrons. Hole transport layer. Guides. On top, a second electrode collects current, ultrafine metal wire mesh on glass, or a second TCO topcoat. All this is thinner than a human hair, yet it turns sunlight into usable power. The layers are precisely engineered for maximum performance. And transparency. That's the anatomy of a toilette. Power-generating window. Manufacturing starts with ultra-clean glass. Any dust can ruin performance. The glass is coated with the transparent conductive oxide, using a process like sputtering in a vacuum chamber. Next, the active solar layers are applied, printed, coated, sprayed depending on the technology. These layers are then treated with heat light. A top electrode is added, fine grid, another transparent layer. The whole stack is sealed, usually with another glass pane to protect against moisture and air. Wires are routed to the window's edge, connecting to a hidden junction box. The result, a durable, weatherproof, power-generating window ready for installation. It looks like ordinary glass, but it's a clean energy machine. That's high-tech manufacturing in action. Before installation, solar windows face brutal testing. They endure extreme temperature swings, freezing cold, scorching heat, to ensure layers don't crack or peel. Humidity tests, moisture tests, check for leaks that could corrode the sensitive solar materials. Mechanical tests, high winds, impacts, proving the window is as strong and safe as standard glass. Only after passing these tests can a solar window be certified for real-world use. Durability and safety are non-negotiable. The result, windows that last decades, generating power through sun, rain, storms. That's peace of mind for builders and occupants alike. So, where do solar windows shine brightest? In the heart of our modern world, our cities. With millions of square meters of glass covering every skyscraper and office block, this immense, untapped real estate is the perfect canvas for transparent solar, turning entire skylines into passive power stations. These windows integrate power generation directly into the facade, offsetting energy consumption and cutting carbon footprints. But the benefits are twofold. The technology is engineered to block invisible infrared radiation, the primary source of solar heat. This dramatically reduces the load on air conditioning systems, a major energy drain resulting in lower energy bills and a lighter environmental touch. The applications extend far beyond skyscrapers. In high-tech greenhouses, they can be tuned to let through the specific light plants need for photosynthesis, while capturing other wavelengths to power lights and irrigation. Our public infrastructure can also become self-sufficient. Imagine bus shelters and highway noise barriers that quietly generate their own clean energy to power lighting and digital displays. This technology is a game-changer for architects. Unlike bulky, opaque panels, transparent solar liberates design, allowing for sleek glass facades with power generation hidden in plain sight. For the people inside, The benefits are immediate. Comfortable indoor temperatures, abundant natural light without harsh glare, and protection from UV radiation, improving well-being and productivity. The next step is combining this with electrochromic technology to create truly smart windows that dynamically change their tint in response to the sun, maximizing both comfort and energy generation. As efficiency rises and costs fall, we're reaching a tipping point. This will shift our urban energy paradigm, turning buildings from passive consumers into active prosumers that contribute to a more resilient, decentralized city grid. The vision is a future where our cities are not just smarter, but wiser, harnessing the sun's energy in an elegant and powerful way. The future is literally clear, powered by the very windows we look through. Transparent solar is here, and it's ready to reshape our world, one pane of glass at a time. Thanks for watching.